Buongiorno, I'm Beaume from the University of Leeds, and I'm going to talk about a probabilistic protocol to assess the control of finite amplitude instabilities, and in particular I'll be applying this to transitional flows. So this is joint work with Pershin from the University of Oxford and Tobias from the University of Leeds. The study of transitional flows dates back to the experiment of Reynolds in 1884, where he was characterizing the flow down a pipe by injecting some dye along its center line. He observed two different types of behavior: the laminar flow behavior, where the dye was flowing along the center line of the pipe undisturbedly, and turbulent flow, where the dye was flowing along the center line of the pipe for a certain amount of time until it got hit seemingly randomly and could disperse along the whole radius of the pipe. He also observed there was a non-dimensional number that could help determine whether the flow was going to be laminar or whether it's going to be turbulent. This number is now called the Reynolds number and involves the velocity or characteristic velocity for the flow times a characteristic length, which could be the pipe diameter, divided by the kinematic viscosity of the fluid. So let me just try and convince you very quickly why it's important to try and control the instability, to try and prevent turbulence, for instance, when we're looking at fluid transport. So we can write the energy lost down a pipe, or how much energy is needed to make the fluid flow down the pipe, as being proportional to this mass kinetic energy, rho u squared, where u is the average velocity, divided by the pipe diameter. And because this is phenomenological, we're missing a lot of physics, we can just say that is proportional to a constant f, which we call the friction factor. And so we can just look at what the friction factor is equal to as a function of the Reynolds number. And this is what's done on this diagram called the Moody diagram, showing this friction factor versus the Reynolds number in a log-log scale. Up until Reynolds number of 2000, the flow is typically laminar and the friction factor falls onto this nice linear curve. Beyond 3000, the flow is typically observed to be turbulent, so it falls along this curve. And for instance, if we want to look at a flow at a Reynolds number of 10,000, we're very likely to observe it to be turbulent, which gives rise to a friction factor of 0.03. However, if we were to be able to maintain this flow to be laminar, we could continue this line to observe that the friction factor at a Reynolds number of 10 to the 4 would be 0.01. In other words, maintaining this flow at the Reynolds number 10,000 would cost 3 times less energy if the flow is laminar as opposed to turbulent. The flow that I'm interested in today is plane quet flow, which is a three-dimensional fluid confined between two parallel walls. The top wall here moves in one direction, and the bottom wall moves in the opposite direction at the same amplitude of the velocity. This flow is entirely driven then by viscous effects, which give rise to this laminar flow profile. And it's very simple to put down in equations because the fluid flow only obeys the Navier-Stokes equation, which is written here in its non-dimensional form, and the incompressibility condition written there. When we write down these equations, it's very easy to observe that there's only one non-dimensional parameter that essentially parameterizes the whole flow, and this is the Reynolds number, as I've introduced before. There's no external forcing term, the flow being driven by the imposition of these boundary conditions on the wall, which are no-slip boundary conditions, taking into account the motion, the differential motion of the walls in the streamwise direction. We'll be talking about control, and the control strategy that we chose to use is spanwise wall oscillations that are in phase. So this is a control strategy that's been used already in the literature to control transitional flows by Rabin, Kofod, and Kurzweil, and to control fully developed turbulent flow by Quadri and Rico. And what we have here essentially is a modification of the boundary condition, which was previously just this motion in the streamwise direction, and we're introducing here a motion that changes in time, that oscillates in time here in the spanwise direction with amplitude W osc and frequency omega. This changes the laminar flow profile by introducing a time-dependent component in the spanwise direction. Plane quet flow belongs to a family of flow called subcritical shear flows, And essentially, these flows are characterized by the fact that the laminar state is linearly stable for all values of the Reynolds number, and I've represented it here in phase space by this dot. Yet, for sufficiently large values of the Reynolds number, 325, roughly speaking, for plane wet flow, we observe long-lasting turbulent behavior. So if we want to sketch this in parameter space, in phase space, this is a picture that we would get where turbulence lies here and the laminar state is there. And because both of these states are attracting, there has to be a separatrix between their basins of attraction. This separatrix is shown in black and is called the edge of chaos, together with two interesting objects along it. The edge state here, which is a local attractor along the edge of chaos, and the minimal seed, which is the perturbation of minimal amplitude from the laminar state to cross the edge of chaos. So the edge of chaos has a property which is actually cursing the study of this instability, of the transition to turbulence instability, which is that it's folded, it's wrapped around the turbulent saddle in such a way that if I take a perturbation here shown in red and I time integrate it forward, what I end up getting is following the edge until I hit its unstable manifold and I get repelled to turbulence. But if I slightly perturb this initial condition and I time integrate here the blue one instead, then I'm following the edge on the other side and get repelled towards the laminar flow, which leads to a stratification of phase space here, whereby very close initial conditions we have entirely different fate. That makes our system a little bit more complicated to study. So if we want to understand how to characterize the robustness of the laminar flow, typically if we have an instability that is triggered by infinitesimal perturbation, we would use linear stability analysis. This is not the case here. This instability is triggered by finite amplitude perturbations. And therefore what we need to know is the global structure of the basin of attraction of the laminar flow. In other words, we want to try and characterize the boundary of this basin of attraction. It's not so easy to do. In fact, an exhaustive knowledge of it is impossible because we're in infinite dimensions. So what we're going to do instead is try to use probabilistic methods to achieve this goal. What we're introducing here is the laminarization probability. So we're going to be drawing spheres around the laminar state here, spheres determined by a radius. And along this sphere, we're going to be drawing a large number of initial conditions, time integrate them, and determine their laminarization probability. And then what we're going to do is draw the laminarization probability as a function of the amplitude of these perturbation, or as a function of the radius of that sphere. The way we draw perturbation is as follows. So this is our initial condition U. It's going to be a perturbation from the laminar state, so we're going to have the laminar state here, and we're going to add this perturbation here, which has a component along the laminar flow direction and a component perpendicular to it. So we set up our simulations in a domain size of 4 pi in the streamwise direction, 2 in the wall normal direction, and 32 divided by 15 pi in the spanwise direction. And we're focusing particularly at a Reynolds number of 500 for now. So we've decided to be interested in a range of kinetic energies for the perturbation that spans 0 to 2/3 of the turbulent kinetic energy. And we've divided that range into 39 energy levels. And for each of these energy levels, we've drawn 200 random perturbations, and which we time integrated to determine an observed probability. That probability is plotted here. Laminarization probability is a function of the energy. And it's got a certain number of properties. First of all, that laminarization probability is 1 for small enough values of the energy, and then it decays pretty much monotonically until it reaches a plateau. So we decided to fit this, this numerical results using a transformation of the lower incomplete gamma function shown there to observe here to obtain the sine curve. So that sine curve is the fitting for 500 in Reynolds number. We observe the green one for 400 and the red one for 700. And what we can see directly here is that increasing the value of the Reynolds number leads to an increase in the sensitivity of the laminar flow to perturbations over the whole range of energies. So then, since we have this laminarization probability now, we understand that it represents a measure of the relative size of the basin of attraction of the laminar flow. It also provides a solid framework to quantify efficiency of control strategies. So we're going to compare these results to those in the case of control. So the results shown here using the bars are those obtained for Reynolds number 500 and a control amplitude of 0.3 and a control frequency of 1/16. So they're fitted using this black curve, and you can compare them to the cyan curve there, which correspond to the uncontrolled case explained on the previous slide. What we can see here is that adding the control leads to an increase of the laminarization probability across the whole range of energies, and particularly this is particularly efficient for large enough energies when we can see that the laminarization probability has increased by roughly a factor 2.5. We've decided to go beyond this and try to characterize the robustness of the laminar flow, or give a criterion to quantify it, which is a simple scalar criterion. So the first one that we came up with is this laminarization score. And what this laminarization score is nothing else than the expected laminarization probability of a given of a random perturbation that belongs to a given distribution of energies, Fe. So if you know in your system that perturbations are generated at a given energy with a certain probability, then you know this distribution and you can integrate P lam times this distribution to obtain this expected laminarization probability, or what we call the laminarization score. For example, here we've selected a distribution that is exponentially decaying with the value of the energy, which means that it's more that lower amplitude or lower energy perturbations are more often generated in our system than larger energy ones. And if we calculate this laminarization score with this distribution, what we observe is what is shown on the diagram here on the right. So this is shown for various values of the amplitude of control, WOSC, and of the frequency here. And we observe two striking things. First of all, there seems to be an optimal frequency for the forcing, which is 2 to the power minus 3, where pretty much all these curves seem to be maximized there. So the laminarization probability seems to be maximized for a frequency of control of 2 to the power minus 3. And also what we notice is that increasing the amplitude, so going from the uncontrolled case in black to the purple case, which corresponds to WOSC equals 0.5, going in the direction of increasing control amplitudes leads to an increase in the laminarization score, which means that this control strategy becomes more and more efficient at killing turbulence or transition to turbulence as we increase its amplitude. So just looking or just maximizing this laminarization score is a good criterion to kill off turbulence altogether without any energetically without any energy considerations. But you might think that increasing the amplitude of the control is going to cost a lot more energy in an industrial process, which might not necessarily be energetically savvy in the end. So we've decided to introduce another criterion, which is the expected dissipation rate, epsilon bar, which is essentially the laminarization probability, the expected laminarization probability S times the dissipation rate of a laminar flow, because we will get to this flow with a probability S overall. And we add to that the complementary probability times the cost or the dissipation rate of the turbulent flow. And when we do this for a uniform distribution of perturbation energies, what we observe are the results to the left, where we essentially observe there is an optimal amplitude for the control. So this is the uncontrolled case. And as we increase the amplitude of the control, this curve shifts down until 0.3 or 0.4 in amplitude, shown in red or green here. And if we increase further the amplitude of the control, that curve goes back up, and we end up at 0.5 on the purple curve here. So that seems to infer that there is, in addition to this optimal frequency to the 2 to the power minus 3, there is a preferred choice for the amplitude of the control, which is between 0.4 and 0.3, for instance here. And that would lead to a decrease in the cost for this flow by 20%, roughly speaking, compared to the uncontrolled case. Now, if instead of having a uniform distribution for perturbation energies, if we have an exponentially decreasing distribution of these energies, then we end up with slightly different results, as shown on this panel here. Instead of being able to decrease the cost of the flow by 20%, we're only able to decrease it by 5%, roughly speaking, with, for instance, WOSC equals 0.1 in blue here, and this this frequency for the forcing, or 0.2 in amplitude there. This result, this more bleak result here, is expectable because this control strategy, as I've emphasized before, tends to control better the larger amplitude perturbations rather than the small amplitude perturbations. And if we have a distribution of perturbations that is exponentially decreasing with their amplitude, then of course what we'd be doing here is spending a lot of energy to activate the control that would be only acting on few perturbations. So to summarize my talk, I've introduced here a probabilistic protocol to quantify the efficiency of control strategies designed to control finite amplitude instabilities. I chose a problem from transition to turbulence, which is plane quit flow, and used the laminarization probability as a way to quantify the structure of the boundary of the basin of attraction of the laminar flow. And as a key result, we've managed, according to certain criteria, to determine optimal control parameter values for the design of a control strategy. What we're working on now is to speed up these calculations. So we have a preprint at the moment on the use of Bayesian inference to try and reduce the number of laminar perturbations that we're considering. But we're also trying to work towards the extension of these concepts to larger domain sizes, but also to test other flows and other problems which are not necessarily related to hydrodynamics, because all we're doing here is characterizing finite amplitude instabilities. Thank you for your attention, and do not hesitate to drop us an email if you're interested in discussing these results or for any comments.